We talked about over and under approximations. We're not done with those. We're going to come back to it. But now we're kind of talking, we saw that those can be annoying if we want to add up. We know the more rectangles we have, the better. But it gets time consuming if you have too many rectangles. So we're trying to learn some strategies that might help us add things faster. So we ended yesterday dealing with summation formulas, just talking about what a summation means. Now we want to talk about how you can add up these things. So the rules of summation. Right, here's my little, if I said, oh my goodness, you're so quick.
No, I can't do the blue, it's too spicy.
If I wanted to add from 1 to n of c a sub I, okay, what that means is c is just a coefficient. So c a sub 1, c a sub 2, c a sub 3, and so on. And you don't have to write this down yet. I'm trying to give you the justification rather than just telling you what it is. And so you add all these up. What does every term have in common? Yeah, and the a just represents some function. But they all have a c, right? We kind of did this when we were calculating our areas yesterday. We knew all the rectangles had the same width, so we just factored that out in front instead of putting it on every single one of them. So if you have a coefficient, that can actually come out in front of the summation. So the formula, the c can come out in front, and then you can take that times what you get when you add up everything else. Second one. If you're adding up these a sub I plus b sub I, so it might be I'm going to add up from 1 to 5 of x to the I minus 3 to the I. And so when you add these, you get an x plus 3 plus an x squared plus 3 squared plus an x cubed plus 3 cubed, right? Could I reorder these because we're adding? Could I put all of the x's together and put all the numbers together? We know we can add in any order, so that's not breaking any laws. So if you have multiple terms, you can add them up individually. And then just add those two sums together. This one, it's kind of a combination thing. So if I said I wanted to add up from 1 to 3, a 4 plus x to the I power. Okay, so if we wrote this out, we would have 4 plus x plus 4 plus x squared plus 4 plus x cubed, right? So kind of using the last one, we could add up the two, all the 4's together and all the x's together. But this one, notice it didn't have any i's in it. So when I'm adding these, I just get 3 4's, right? The 3 coming from here. If you're adding up a constant, you're just having the same number n times. So this is just n times a, because a is a constant, so you get an a every single time, plus the sum from 1 to n of my b's, sub i's. So the last one, what happens if you add up 1 n times? What are you going to get? 1 plus 1 plus 1 plus 1, right? It's a constant. So when you add that up, it's n times 1. So we just get n. If I'm adding 1 up from 1 to 10. It'd be 1 plus 1 plus 1, 10 times. So we get a total of 10. Okay. Then we have some common formulas that we need. So we see a lot adding up powers of I. And I use this example in a few of mine, but this just means like 1 to some power plus 2 to some power, 3 to some power. So what's happening here, the power doesn't change, but my base is different every time. We are going to look at the 3 most common forms, something to the first, second, and third power, and talk about how we can quickly add those things. So rather than just give you formulas, I want to kind of explain to you where they come from, or at least the first one. So here's my little justification, and you don't have to write this down. So if I'm adding this up, you have 1, 2, 3, plus 4, and it keeps going until we get to n, right? So we would have n minus 3, n minus 2, n minus 1, n. That would be the stopping point. Okay, so we want to know, is there a fast way to add these up? So I want you to look. If I add the first and the last, n plus 1. What happens if I add the second to the second to last? N plus 1. If I add these, n plus 1, these, n plus 1. So we compare them off, and we're getting n plus 1 every time. Okay, so the question is, how many times do we get that? So how many terms did we have in our list? N. But then we had to divide that by 2, so because we put them in pairs of 2, right? So we have this n over 2 times. So the actual formula for adding up powers of I is n times n plus 1 over 2. If you're just adding up something to the first power. You will need to know these formulas, so there's 3 of them. I would highlight them, maybe make yourself some flashcards. You'll need to know these before you get into your next test.
Can you go back?
Mm-hmm.
Where did you get n minus 3, n minus 2, n minus 1?
Okay. Let's say if I were adding up. So here's my nth term. This is 1 less than that, so n minus 1. 1 less than that would be n minus 2, n minus 3.
So instead of writing 7, 8, 9,
Yeah,
10,
just because I was keeping generic. I was going up to some number n, whatever that might be. But yes, those would be equivalent. If my n were 10, this would give you those same things.
why would you just write 7, 8, 9, 10?
Because the original problem I was telling you, if it went up to n, not to 10. Because I wanted this formula to work whether I was adding up from 1 to 10, or 1 to 100, or 1 to 1,000. I was just trying to justify.
Is this going to make sense later?
You just have to be able to use the formula. I'm just trying to show you where it came from, so you didn't think I just made it up.
So I don't need to know how this...
You don't necessarily have to know how I got it if you don't like my justification.
Because I literally have no idea what you're talking about right now.
Okay, I was just giving you a shorthand. So like if you look at this.
As long as I don't need to know how this is a thing,
No,
then I
this
don't
was
care.
just
Like,
my
that's fine.
why. That is just showing you that you could pair them up. 10 plus 1 is the same as 9 plus 2, is the same as 3 plus 8, it's the same as 4 plus 7, and 5 plus 6. And so I was just talking about how you can add faster if you pair them up like that. That's where the formula comes
Yeah,
from.
that makes absolutely no sense. So you keep that to yourself, okay?
Whoa, that's rude.
No, like I'm just saying that is not something that I'm probably, I don't know.
So the I squared formula, it is more complex for justifying, so I'm just giving you that one. I only to show you the first one to kind of give you some idea of where it might have came from. But you have to know these three formulas. So if you're adding up powers that are squared, then it's n times n plus 1 times 2n plus 1 over 6. And I cubed is n squared times n plus 1 squared over 4. Alright, everybody highlight this slide or something so you make sure you know it. We are going to spend the rest of the day today using these formulas to add up things.
Do we have to know the other one too?
The properties, yeah.
So we got to know 7.
Yeah, I mean the others you're not going to have to necessarily write out the rule, you just have to know how things work.
I'll highlight that. I think I probably should memorize that.
So I wanted to show you how we would use these formulas. So we are going to add up the first 10 positive integers. So the sum from I equals 1 to 10 of I. Well, the formula I had you write down is n, what's my n,
10,
times n plus 1
11.
divided by 2. So 10 times 11 divided by 2 is 55. Alright, quick check to see if you believe me. Grab a calculator. What's 1 plus 2 plus 3 plus 4 all the way up to 10? 55, it works. Okay. Now, I want to add up the squares. So I'm doing the sum from 1 to 10 of I squared. So the I squared formula, n, what's my n?
10,
Times n plus 1
11,
times 2n plus 1 divided by 6. What do we get? Okay. Check it. What's 1 squared, what's 2 squared, what's 3 squared, what's 4 squared, all the way up to 10 squared.
Oh, this was on our homework actually. $285.
285 or 385? Did you add in 100?
385.
Okay.
I read
See?
the number wrong.
I want to do the cubes. So the cube formula is n squared, so 10 squared, times n plus 1 squared, so times 11 squared, divided by 4. What do you get?
I got 30.25.
So now we can add things up, and I think we could agree that this is faster than when I have you check them, and we're only adding up 10 things. So I could use this formula to go from 1 to 1,000. Something that it wouldn't be feasible to sit and try to add those up on your calculator, but we can use the rules to add them up much faster. Okay, so let's try to extend this. If I want the sum from 1 to 10 of 7i squared minus 5i, so we have to kind of use our properties. I told you with the summation, we can add up each term separately. This has a minus in between, but we can essentially add up the first term and subtract what we get when we add up the second term. I also told you that if you have coefficients, you could pull those out in front of your sum. So this is 7 times the sum from 1 to 10 of I squared minus 5 times the sum from 1 to 10 of I. So, what's the I squared formula? N, which is 10, times n plus 1, which is 11, times 2n plus 1, divided by minus 5 times, what's the I formula? Times 11 over 2. So now we just have to calculate this.
I like it when we get actually real numbers
It's kind of refreshing, isn't
and
it?
not like some eyes.
And it, I mean, it would be annoying, but you could really check it if you wanted to. You could go back and plug in all the things.
That's what the back of the book is for.
Oh. So what do we get?
330? Yep.
24.
Oh, I didn't do the times actually.
Oh.
It'd help if there's like brackets on here instead of just a lot of double parentheses
Yeah,
the whole time.
that
And
is
I
kind
didn't
of
forget to close one.
Alright. So
But it
far,
was
so good?
brackets. Never mind. It's just a pain in the butt getting this has to be like second.
That was the worst one.
Yeah, they're not easy to find. Alright. Do you guys think we can try this one, or should we do one more on our own first? Or one more together first? We'll do this one together, and then you can try the next one. So, when I do this, I can do the sum of each piece separately. So it's the sum from 1 to 5 of I cubed. Can I go ahead and write this as minus 3 times the sum from 1 to 5 of I plus, okay, sum from 1 to 5 of 2. Alright, so my I cubed formula, what is it? N squared, so 5 squared, times n plus 1 squared, so times 6 squared, divided by 4. Minus 3 times, what's the I formula? 5 times 6 divided by plus. Alright, how do we add up a constant?
Add it. No, you do n.
Yeah, it'll be 5 times 2. Because you have 2 and you're adding it in 5 different times. So 2 times 5. Alright, see what we get. We'll check my math. I did that one. You guys get 190?
Yeah.
No, actually I got syntax error, but that's just because I entered. I did something extra with parentheses when I was supposed to.
Okay. Closed more parentheses than you opened, probably.
Probably closed it once whenever I wasn't supposed to.
Alright, you guys try this one. Alright, let's see how we did.
Started.
So you add up 5 8 times, minus 2, the formula for j to the first, so that would be n times n plus 1 over 2, so 40 minus 72, so negative 32. Ooh, 32, right?
Yep.
Any questions on that one? Okay, let's try the next one. Last one like this. Do we have a formula for adding things inside this parenthesis with a square on the outside? No. So we can't just assume that I could add up the stuff and then square it at the end. What should I do instead?
Foil.
So this would be 4k squared minus 4k plus 1. So we have 4 times my formula for k squared. What would that be? Yes, 4 times my formula for k to the first.
10 times 11.
Plus, how do I add up 1 10 times? Alright, here we go. Thousand 330. So I want to talk about how we could use these for some of the things that we've already calculated. Did I get that one?
I just wanted to make sure I put that right.
Oh. Alright. I want to look back at our first example from yesterday. Remember we were adding up, we did it with both 5 and 10 rectangles. And let's just talk about, let's do the 10 rectangles. So when we did the underestimate with 10 rectangles, so kind of shorthand, underestimate, I just put a line underneath for under. Overestimate, I put a sub 10 meaning 10 rectangles and a line over the top for overestimate.
Why is it A?
Area. Alright, so when we did these, think about what we did. We took all of them times what? The width, which when we did the 10 rectangles, my width was 3/10. So we have 3/10 times the sum. We went from 1, how many things did we add up? 10. Okay. Let me show you something. When we did the underestimate with this one, the first number we plugged in was 0, right? And it didn't give us anything. So could we agree I could leave that one out? And after the 0, how many more numbers did we have? 9. So for the underestimate, I'm going to go from 1 to 9. Okay. Now my function was x squared, right? And so if I'm going to add up my I, these would have an I. So the first one I plugged in was 3/10, and then we had to add 3/10 each time, right? So the first time we plugged in 3/10. Next time we did 6/10, which is 3/10 times 2. And then we did 9/10, or 3/10 times 3. So we're really doing multiples of 3/10. That's what we plugged in. And then the formula was to square. So let's see if we can use summation rules to deal with this. We would have to go ahead and square everything. So 3 squared is 9 over 100, I squared. And the 9 over 100 could come out, so that gives me a 27 over 1000 times the sum from 1 to 9 of I squared. What's the I squared formula?
N times n plus 1 times 2n plus 1 over 6.
Let's see what we get when we plug this in. Oh, because we did one with 5 rectangles. Alright, did you guys get 7.695? Is that what we got yesterday for our under approximation with 10 rectangles? It is. So, was this faster? Maybe, maybe not, but if I wanted to do 50 rectangles, would this be faster? Absolutely. Alright, so let's talk about what's the difference for the overestimate. We still have a width of 3/10. But the first one, I didn't start at 0 with my overestimate, did I? I started at 3/10. And then how many things did we have total? 10. So it's just the same thing, except this time we're going to add up from 1 to 10. So 3/10 I all squared. So we did 27/1000. Sum from 1 to 10 of I squared. I squared formula n times n plus 1 times 2n plus 1 over 6 and we get 10.395. Same thing we got yesterday. So we will practice using that more tomorrow. I just wanted to show you how we can use the summation rules with what we have so far. I want to do one last slide, and then I'm done for today. So I want to calculate this limit. So we've never had a limit where we're adding up an infinite number of things before. But we can use summation rules to help us. On the top, 1 plus 2 plus 3 plus 4 all the way up to n. Isn't that just adding up powers of I? Okay, so that little part on the top, that's like saying the sum from 1 to n of I. And don't we have a formula for what that adds up to? Yeah. What is that? Can I just put the 2 on the bottom with this n squared? Is that okay? Bear with me so far. So how does this help me? What can I do from here? Okay. We have lots of rules for evaluating things like this. So we could, let's go ahead and distribute on the top. So we get n squared plus n over 2n squared, or you could even reduce an n, couldn't you? Would that have been easier than distributing, maybe? I guess it's kind of toss-up either way. Let's do that. Can I cancel an n instead? Take out one of those. So then I have n plus 1 over 2n. So then it's infinity over infinity, so you can do L'Hopital's, you can do the trick to divide everything by the highest power of n. So you get 1 over 2. So this is 1/2.
I figured 1 over 2.
L'Hopital's derivative of the top and derivative of the bottom. Derivative of n plus 1 is 1. handout for you.